Let's look at the physics of a playground swing and how we pump it to get higher. The basic mechanics is not hard to understand, but a lot of the explanations out there seem to miss the mark. I'm going to use a model from this 2023 paper by Harada et al., in which we approximate the human body as 3 segments. I'm going to assume for now that the chain is rigid and doesn't bend, but the basic pumping principles are going to be similar either way. This is what happens when we run the model forward in time. While this is just a model with a handful of lines, it really does resemble how a human would pump a swing. Here's something interesting. When you learn to pump a swing, often the first thing people tell you is to throw out your legs. But look at the simulation on the right here. Pumping works almost as well without leg movement. This is because the weight of your lower legs is negligible compared to the weight of the rest of your body. Here's something else interesting. You can pump a swing in reverse to slow it down if you invert the timing of when you lean. And the reduction in amplitude on each cycle is approximately the same as the increase when we pump the swing forwards. The basic mechanism is actually quite simple and has to do with moving your center of mass. The red dot here shows the center of mass position in each case. Actually, this is the combined center of mass of swing and swinger. By leaning backwards, we shift the center of mass backwards. Conversely, by leaning forwards, we shift the center of mass forwards. Have a look what happens if we lean back for the whole cycle. The center of mass position goes back and forth normally like a pendulum, but the chain travels higher up on the right side. What if we could then pull our center of mass up towards the chain, and now we've got more energy in the swing? But hang on a moment, how do we pull up the center of mass from inside the system? Internal forces can't change the center of mass of a system, so if we pull on the swing, surely the swing will just move in reaction. Well, the swing does move in reaction, but there's still a net movement of the center of mass. This is possible because there is an external force on the system, the reaction forces at the pivot and ultimately into the ground. In the real world, there's 2 approaches we could take. The first is to move quickly near the ends of the motion. This maximizes the advantage of shifting our body, but results in significant reaction forces on the swing that work against us. The second approach is to move as smoothly as possible. This reduces the reaction forces, but it doesn't get the maximum advantage from leaning. Now, actually, both of these produce quite similar results in simulation for the rigid swing. If you really want to get the maximum height increase per swing, it's a pretty complicated optimization problem. If you just want to have fun on a swing, it doesn't really matter. As usual, there's more detail in my blog post, and I talk about why this model also applies quite well to a swing with non-rigid chains.